So let's go over this example. Accelerating a crate. Let's go over this example. A truck is accelerating at a rate of positive 1.5 meters per second squared. This is the acceleration of the truck. The mass of the crate is 120 kg and it does not slip. So this means that the crate is also moving at the same acceleration, the 1.5 meters per second squared. The magnitude of the displacement is 65 meters. Calculate the total work done on the crate by all the forces acting on the crate. So on the truck, because this is okay, maybe do this. When the truck is moving on the right, due to the weight of the crate wants to move in this direction, but then there is normal force, there is the weight, so we need to find the forces here. So again, there's friction pulling it this direction, so it's Fs, friction, force due to friction, and here would be the force due to the normal, and we'll have the weight. So mind that this truck wants to move this direction, that's why we have friction going this direction. So okay, and then the angle between displacement and the normal, or and the normal course, this angle is 90 degrees. So when you go to substitute the equation of the work done, put 90 there, and then you have 0. So the angle between displacement and the weight is also 90. It's actually negative 90 degrees, but a cosine of a negative is just the same as the cosine of positive. So now, so that's why we have this as well. And then the angle between the displacement and friction force, displacement and friction force, is this. It's in the same. It's okay. Maybe the displacement is along this direction, and then also the frictional force is along this direction. So the angle between the two is 0. So that's why we have this, because cos 0 is 1. So now of a moving object, this is why we have it like this. The acceleration, we are given the acceleration because the acceleration of the truck is the same as this, it's the same as the crate. So, and then we have the mass of the crate, so we can determine the force. So now when we substitute to the equation of work, which is force times cos theta, and then this times displacement, so we have, because it's also of the same, it's parallel to, displacement is parallel to the force applied, so we have 0, and then they substituted the force, which is 180, and then the displacement, which is 65. So now because we are required to find the total work done on the crate by all the forces, so the work done, the total work taught, and call it taught, would be the work done to be you add all the work done, all the work done on the system, so in order to get the total. So in this case we have the work done due to the normal force, and what we have the work, and what did we have also, due to the weight, the work done due to the weight, and then we have the work done due to friction. Then you sum all the work done. So this is what they obtained. So you do this example, and this is what I was saying. So the total work, when several forces act on an object, the total work is the sum of the work done by each force individually. For the rigid object with no rotational or internal motion, okay, remember I said this is the equation of the work done. Now this is what I mean. So because you remember you can sum forces, and this, if you can sum forces, let's say F net, the net force is equal to the sum of all forces, and then from this equation you can clearly see now that when you substitute the summation sign of the forces, then this actually means that you can sum actually it's F minus F cos theta. This means that you can sum the work as well. Okay, this should be in combination. Oh, this is what they mean. Yeah, this is what you can sum. You can sum the force. If you can sum the forces at a certain displacement, it means that you can sum the work. So it's due to that. So let's go to this example 6.2. Diane pulls a sledge along a snowy path on level ground with her little brother Jasper riding on the sled. The total mass of Jasper and the sled is 26 kg. The cord makes a 20-degree angle with the ground. As a simplified model, assume the force of friction. On the sled, and then force of friction, and then sled is determined by the frictional constant, which is 0.16, even though the surfaces are not dry. Find A, the work done by Diane, and B, the work done by the ground on the sledge while the sled moves or displaces 120 meters along the path at a constant speed at 300 km per hour. What is the total work? What is the total? So by here, now since constant, it means acceleration is 0. So have that in mind. Also see what is the total work done on the sled. So A, we are required to find the work done by Diane. So let's sum the forces along the x direction. So here we have, so this, by now I think you're very familiar with doing this. This is negative due to this direction, and then you add this t cos theta somewhere here, this t sin theta over here t cos theta, t sin theta. So you add this and the friction, so you equal to 0, as this thing moves with a constant speed, means 0 acceleration. And then on the y direction, and the y direction, that means this direction. And then for some forces, so we'll have to deal with this component of tension, and then the one going down, mg sine theta, or mg plus n, the normal force. So when you sum that, should be 0 because it is not moving along the y direction. So that's why we have 0 here. So 0 acceleration along this direction due to that. So now we given the frictional force as this. This is how we do the frictional force. Substitute Fk into the equation 1, which is this one. You substitute it here to substitute this equation here, and then multiply. You need to multiply. Stop. Okay. Then multiply equation 2 by mu k, so that actually what we're trying to do is to eliminate the ends. So when you multiply this equation by mu k, so that this will, when we add them, this one will cancel this one. So this will be the next step. So then adding now, so we eliminated the mu kn, so this will be the final equation, and then we're solving for T, the tension, the magnitude of the tension. So this is the force we'll be putting into the equation of work. So now that we calculated the force due to the rope or the tension, so because now we have T, and then we need to determine the component now that it's in this direction. So that's why we have this along the x direction, the displacement along the x direction, and we have worked out the tension here, which is 41 Newton, and then the angle is 20 degrees, and then remember the displacement, which is 120 meters. So this is the work done due to the tension, or due to the tension caused by Diana pulling the rope. So B requires us to the work done by the ground on the sledge. Okay, so work done by the ground. Okay, so work done by the ground. So the frictional force, okay, cos theta, the component that's parallel to the displacement. So times, so we want to, this is the component of the frictional force that is parallel to the displacement. So when we want to find the work done due to the ground, we'll multiply this by the displacement, and then it is applied, and this must take note. The work done with the force applied is 180 by the ground. So I'll say it's always safely I'll say it's always 180 degrees. So must not only apply force by the ground, but talking about 180. So this is why we have 180 here. and then cosine 180 is -1, so that's why we have this reduces to this equation, and actually, so here this is to be the fk. It should be the fk. So you substitute it. To this equation. So finally, we have this equation, except the negative sign. The work done due to the ground is the same as the work done due to the tension. Yes, because you can see, okay, you can see now, but don't always assume it, but you can see because the tension, okay, the tension, okay, first of all, the displacement is along this direction, and then the tension goes this direction, and then actually, and the ground as well, and the ground this direction. So here, this is what it means, that they are the same. This and these are the same except for the direction, but don't always assume that. I'm not sure if that's always the case. I need to check it. So then the total required to find the total now. What is the total work done on the sled? So now we need to add the work done on the due to the ground or due to Diane. So we need to add those. So this is the work done due to Diane. It's the work done due to the ground. So when you add them up, find out the total work done is 0. Maybe just to waste time, I'll say. So the work done due to the tension from Diane, and then by the ground. So this is why the total work done is 0, and this also explains why the sledge is not accelerating but moving at a constant velocity. I think this is what I wanted to add.